us today. Thank you very much for dropping in today. I'll do a really quick introduction. I'm not going to steal any thunder, though. I'm not going to introduce your talk. I'm going to introduce you and then let you take it over. Dr. Kelly Rose, PhD in Geo Data Science, with 20 years of service and research experience in U.S. Department of Energy's National Energy Technology Laboratory. She is also a technical director of NETL's Sciencebased AI ML Institute. Her research focus is on developing novel science-based data-driven methods and models for addressing energy and environmental challenges, including NETL's award-winning Energy Data Exchange. Dr. Rose leads the collaborative team to deliver impactful computational data science resources and models in reusable, scalable, and reproducible formats. Her work has been applied to many scientific and societal domains, including earth science, geoinformatics, research data management and visualization, climate, oil spill prevention, mineral and groundwater resources. Wow, a lot of the spatial. Now, I wanted to just, one more thing I want to mention here, and I thought this was really, really cool, is that Dr. Kelly Rose has co-authored more than 100 public data sets, models, tools, journal publications, and technical studies. And so we love that whole idea of publishing data sets and the models and so forth. I won't go on any further. Dr. Kelly Rose, I'll turn it over to you to go ahead and introduce your talk, and then afterwards we'll have some questions.
Sounds good. I appreciate everybody joining today, virtual, and we'll look forward to the discussion at the end. As Michael said, data is kind of the foundation for a lot of things that we all do. We're generating data, we're consuming data, and this is a data generation, a data era that we're living in. The opportunity to resurrect historical data and put it back to work to drive next generation solutions for a wide range of complex societal and environmental and environmental engineering needs is substantial. So today, I don't like the introduction foreshadowed, the team that I work with, we actually occupy locations all across the country at this juncture. It's a virtual world. We've always operated in a more virtual way. It's one of the luxuries of the data science realm. I have a lab and field background as well as computational. I spent years sailing the 7 seas, working on drilling and coring expeditions for natural gas hydrates related research studies, as well as other things before I downshifted after the Deepwater Horizon oil spill, which we'll come back to at the latter half of my talk. And I pivoted directions at that juncture, which is really where things that we're going to cover today started to emerge. And the last 15 years of my career has really been focused on this theme of data, resurrecting data, putting it to work, and doing novel things with it. This is not Morgantown, West Virginia, that's NETL, where I work, the National Energy Technology Lab. There's 17 national labs within the US DOE. And for the students here on the line today, I wanted to point this out. We're rolling into the summer, intern season. Many of my colleagues at the national labs are recruiting. You can look for recruiting opportunities, both full-time and intern at NETL using the URL down here at the bottom. There's a AI-free update that you can register for, or you can just click on the historical ones, and we offer job postings, intern postings, etc. But you have to go to the other national labs websites and look for their postings as well. And I'm advertising them because there's a lot of work going on right now. There's a lot of opportunity for you to experience research in a non-academic setting or in collaboration with our academic partners, which is what the national labs tend to do. I'm actually based out here in Albany, Oregon. I spent 9 years back at our Morgantown facility, and then I migrated west, followed the Oregon Trail. Yeah. If you played that really old video game. So data science is not done in a bubble, folks. It takes a team, and this isn't even my full team, and this is pre-pandemic, as you can see by the absence of masks, and we're all standing together. But this is the year right before COVID hit, and this was our summer team that was physically in Albany, but I've got folks that I collaborate with all over the country, and in some instances all over the world. Collaboration is key. AI and ML, you'll hear that acronym come up, and I think it's probably pretty normalized in most people's nomenclature now, but artificial intelligence, machine learning, It's part of our daily lives. We actually don't even realize half the time that, it's helping us figure out where there's traffic congestion. It's, Tesla's self-driving cars, the social media ads that pop up online in our smartphones. It's all over. The recommendation engines for everything from shopping to videos to books to music. All of this is AI driven. These are really well documented technology, commercial AI ML kinds of activities. They're also I like to think of them as fairly linear. When we talk about energy, environmental, engineered systems, they're more complicated. There's a lot more going on, but the opportunity to apply AI ML and data-driven, data science-driven methods, it doesn't all have to be artificial intelligence, is continuing to crescendo. And this, you can tell this plot is out of date, but even as early as 2010, you started to see an uptick, and that was because of access to data. Scalable data, relevant data, and in the research realm, not just the commercial sector, the tech sector, but in the research realm across all disciplines. Artificial intelligence, machine learning, data-driven analyses and studies were really starting to take off, and now they're really roaring. It's a tool, it's a capability. It doesn't mean you have to be an expert in AI ML and data science, but being able to partner and speak some of that language with your colleagues is actually really important in this era. Andrew Nigg out of Stanford has recently been quoted as saying, overcoming limited data AI challenges requires combining subject matter expertise with data and computing. Well, duh, this is science-based AI ML. In complex systems, being able to take the physics that we understand about those systems or the science, the theory behind what we know about complex systems like the environment, like engineered environments, etc. These models and the knowledge base that we have cultivated in the different science disciplines is still incredibly valuable. And we are data limited in many of these domains, but when you combine the data with the contextual knowledge and expertise from disciplines like petroleum engineering and geosystems science, etc., you can start to make breakthroughs in a number of ways for applied AI, as well as even more fundamental AI related breakthroughs. I set the stage with that sort of broader context, but we're going to dive into an example going forward that I hope helps illustrate the potential and maybe even piques your interest coming from your department and subject matter area expertise. Put your own thinking cap on, put yourself in sort of the shoes of, oh, how could I use AI ML or partner with a colleague that has that expertise to resurrect information from the past and make breakthroughs for the future that are really timely for the now. There was a study done back in 2016, so this is getting a little bit stale, but it actually still pretty much persists. 80% roughly of researcher time, data scientists' time, is spent at what we call the bottom of the data pyramid, finding appropriate data, relevant data, getting it onto our devices, out of journal articles, off of other websites, out of old server files, heaven forbid, off microfiche film and other outmoded data, storage media, transforming it, getting it into the same units of measure, double checking it, making sure that it's integrating properly. And as you scale up and get more and more of this, you need to be able to optimize those processes, trust the algorithms that you're developing so that you can do this at scale, not just on an Excel spreadsheet, which taps out at about roughly 1 million features or so, but something that is truly scalable and allows you to then take advantage of science and physics-based knowledge in context with this type of data to do more with it. But data is the fundamental starting point. It's the energy for analysis and inquiry, like we like to say. And right now, a lot of researcher time in all disciplines is bogged down finding relevant information and getting it into formats that are going to be consumable. And everybody has a slightly different need. So ontologies and standards only take you so far, and the opportunity to do more with algorithms and tools now to resurrect and convert this type of information more rapidly and chip away at that 80-20 balance, and maybe even eventually invert that 80-20 balance so we can get to the work of the fun work of using data to answer questions, is one of the things that my team works on. We work on answering those questions too, but we spend a fair bit of our time still trying to get the data, and we consider ourselves data detectives, data resurrectionists. Wellbore Data is one of the data sets that we rely on heavily at NETL. We're a fossil energy carbon management aligned laboratory, which means we work on environmental, social, and energy related problems tied to conventional fossil fuels, coal, oil, gas, and the legacy of those, as well as new carbon negative, carbon zero technologies like capture, storage, direct air capture, et cetera. Unconventional rare earths, critical minerals, hydrogen storage. There's a lot of other application spaces that we get into, but one of the things that's fundamentally aligned to many of those areas when you're talking about the actual resources themselves, whether it's storage or extraction of energy resources, we need to know more about the Earth's subsurface. And our best tool for understanding the Earth's subsurface comes from wells. There's actually over 6 million well records that I've been able to find. I did a study that concluded in 2016, assembling the deep drilling record, not groundwater wells and geotechnical wells that are in the upper, say 1,000 meters of the Earth's crust, but deep drilling records that go from about 1,000 to about 40,000 feet below the Earth's surface. I know I just switched units of measure on y'all. Imperial to metric, sorry. And there's at that time in 2015, there were over 6 million drilling records. Not all of them had spatial information. So you see on the map here, there's about 5.6 million data points. It's a legacy. It's a legacy of our species' exploration of our subsurface within the crustal zone of the Earth. Still relatively shallow when it comes to the Earth's subsurface, but in comparison to what we know about the surface of the moon, where we have the ability to visualize, remote sense, acquire information in real time, time series monitoring, et cetera, our ability to do the same type of exploration, imaging, and analysis of the subsurface of the Earth that we tend to interact with every single day in highly engineered applications for extraction, injection, exploration, discovery, we still really don't have great information about the subsurface because the data is so disparate and so fragmented. But we're starting to transform that and move past that bit by bit, little bit by little bit. The infrastructure bill that was passed in November is actually catalyzing even more interest in this collection of knowledge and information that is still highly disparate, but slowly coming into focus, and this will help accelerate it. There's a number of different studies related to mine waste remediation, accelerating carbon capture and storage technologies. There's also a huge chunk of funding that's tied to dealing with appropriate abandonment of aging infrastructure like Orphan Wells. These resources that we've been emplacing in our Earth's subsurface, they age just like we do. And when they age, they get decrepit, they tend to fail. They can cause problems. They are an opportunity for knowledge and interaction with the subsurface, but they also are a bit like opening Pandora's box. You're not always sure what is down there and how we've perturbed that environment. It's no longer an in situ pristine condition. As soon as we interact with it, we've disturbed it. And our ability to do a better job of reusing these resources and or abandoning them appropriately relies on the use of this data set. The earliest wells were actually drilled for deep salt brines, but the first oil well actually was initiated in Salt Creek State Park in Western Pennsylvania, just outside Pittsburgh. This is reportedly a photo of that well, and it is a relatively shallow well, but it is an oil well. But early records are pretty poorly maintained, but they also tend to be pretty shallow wells. We know where people were drilling. Even if we don't know every single spot because they weren't keeping good records, we have a pretty good sense of where these activities were happening. We didn't have the ability to do remote sensing in the subsurface or forecast what was down there. So the only tool they really had was sort of like the doctor poking at you going, does it hurt? Does it hurt? Is it here? Is it here? Water, oil, gas? This is one of the videos, just give me 2 seconds. This is a time series video that shows the exploration of deep drilling over about 150-year record. You can see the footprint and the records themselves gain in robustness as time goes on, but it's pretty shocking. By the 1940s, the US and North America as a whole is pretty well covered at this scale of resolution. Obviously, if you zoom in, these points are less dense. What changes over the time series is the depth of investigation. The footprint by about 1940, 1950 is pretty well established worldwide. Then we start deepening our investigation of the planet. So here's a time series shot from about 1940, right before that explosion really took off. And you can see that North America is pretty well established. The footprint is here. Even California, on the West Coast, this is just outside of LA, it's a National Geographic's image, was highly densely drilled at one point in time. And if you fly into LAX airport, you can still see the pump jacks jumping around as you're driving out of the airport because from some of these old oil fields that are still producing to this day. Huntington Beach in 1960 looked like this. I don't think that would pass in today's world, but this is emblematic. Why so many wells? Well, I already gave it away with the probing. We needed to drill in order to understand what was going on beneath our feet. So what you see, if you look at this outside of the spatial context, this is a histogram by year of the drilling record that is known, that is documented. Misassigned wells without any year were given a record of 1901 in the databases that we were working with. So this is a misnomer, but it's, if you know that, you can deal with that in the data itself. You can see that socio-political, economic related activities have a real impact on the drilling record. No shocker. I mean, if anyone's read the prize, we know there's boom bust cycles all throughout this industry's history. But you can also see that record similar to the spatial footprint of deepening wells coming into play. And that's a hallmark of technology breakthroughs. In particular, rotary drilling came along in the late 1890s. Steel casing to keep the wells from collapsing in early 1901. Halliburton filed the first patent for cement isolation around 1920. Hydraulic fracturing actually was first invented way back in the 1940-50 kind of time era, but it was really put to bold use in the early 2000s, initially with tight gas sands and other resource plays, and then eventually the shale gas boom took off in the 2007 kind of era onward. So you can see how these technologies really impact the deepening of wells and the activities themselves. I'm referring to most of this data as oil and gas exploration because based on the information that is available, and not every single record had a well type associated with it, but 55% as of 2015 were classified as active hydrocarbon producing wells. 24% of the well record were abandoned. There were 15% of the records that were unclassified, meaning there was no information available as to why they were drilled, but they were most likely somewhere in the hydrocarbon realm. 4% of the drilling record, quote unquote, well records were locations, likely hadn't been drilled yet, but may have been by now. And 2% were others. That flag for new methods of exploration denotes a change in our ability. Instead of poking and prodding, even that picture from 1960 in Huntington Beach, California, around 1960, 1970, we started using acoustic, seismic, and other geophysical methods beyond wellbore geophysics to understand what was going on beneath our feet. They're indirect detection methods, but it added another tool to our toolkit. The beauty of wells is they are our one direct conduit into the subsurface. They offer us a treasure trove of information and data. And again, it's still relatively disparate, this information, but it is a vast archive of information that we can continue to tap into. And with more folks at universities like yours, that are digging into this information for your own studies, more and more of this data will get resurrected, more and more will become part of the public record and be curated. As Michael said in the beginning, I'm a big proponent for publishing your data. We maintain a data publisher at NETL called the Energy Data Exchange, or EDX. But there's other data publishers out there, RE3 Data, OpenEI, data.gov, et cetera. And most journals now require data sets associated with journal pubs to be published. And that's going a long way to chipping away at this need for high tide to lift all boats, for data to be remain accessible and reusable, even if it does still take work by the reuser to get it into the format that you need it to be and to use it. But the opportunity to resurrect these Wellbore data sets and do more in the future is substantial. These data are still coming from numerous and often incompatible sources. Even something as simple as where are these wells in the US is a real pain. State, federal, and tribal entities still are the primary producers and owners of these data for wellbores themselves. And they maintain them using different standards, different API formats, which is the well identification number. But there are some commonalities, and there's more and more methods and tools available using AI, ML, and data science methods to overcome those challenges. They're at multiple scales. The seismic data and even the wellbore geophysical data represent indirect data sources, but they're still valuable. There's often missing data. It can be remote. Some of the information in even well construction reports and stuff is not always in a format that's as nicely structured. It can be in old PDF formats and what have you. But again, with natural language processing, TensorFlow, neural network related tools for image processing and information extraction, there actually is more and more opportunity to resurrect this information and tap back into the knowledge and understand things about the wellbores themselves, their construction history, the reservoirs, and use the data from the subsurface to improve our prediction about areas that don't have any data at all. Knowing that I was speaking with an engineering group, I'm going to throw a little bit of a challenge question at you all. I just did a back of the envelope calculation at one point in time when I was working on this wellbore data set, just aggregating this world wells database just to understand where are they, how old are they, how deep are they, the basics. I didn't even get to dive into some of the real detailed information. But knowing the history of when casing and cement came into use, I did the back of the envelope calculation and estimate without any multiple casing strings, just single, assuming a single casing and cementing string, and using the age of the wells and the depths of the wells that I had in the database that I've assembled, and using just purely linear math, because I didn't want to get into volumetrics on something that was so back of the envelope. I estimate that we as a species, not only have we burrowed into the subsurface over 6 million times around the world at various depths, exploring and prodding and poking our way down there for resource production, subsurface storage, and just basic exploration, but we have emplaced an estimated 7 million linear kilometers of cement and casing over that period of history. It would be interesting to see if somebody can put a little bit more robustness to this. It would require understanding when multiple casing strings came into play, and this is more in the engineering realm, but it might be something, if somebody's feeling geeky one boring, Saturday night, they can play at. But if you take just the linear estimate, that means that we've put enough steel and enough cement into the Earth's subsurface, including atmospheric, gases and atmospheric isotopic signatures of the now. We have actually mixed that into the subsurface enough to account for over 20 trips to the moon. And we're continuing to interact with the subsurface. While the majority of the history up until now for 160 years is focused on resource extraction, pulling oil and gas out, we have injected water, we've injected frac fluids, we're increasingly looking to inject compressed air, hydrogen, even water for storage purposes, CO2 for sequestration and climate change, and impact reduction, as well as heat extraction on the geothermal front. We are increasingly mixing the crustal signatures with the surface signatures of the planet of today, and we are perturbing the subsurface every time we do that. There's big opportunities with these wells for reuse, but there's also risk. And understanding those environments better is going to be incredibly important for the future. This is a complex diagram, so I'll walk us through it, and you know, please don't get too overwhelmed. But this is a density map of, in this upper piece, we took the northern hemisphere of the full density map of drilling using 1 degree cells of well density by location. There's North America with lots of well density and well drilling. And we ran a jagged cross section through some of the most densely drilled regions of the world. So that's what the spotlight line is that you see. So you can see the highlight of the cross-section density. More density is darker colors, less wells are lighter colors. White is no wells. You can see depth varies. Deepest depths in the dark blues, shallower, and the mean depth of wells along this cross-section line is shown in the white dashed line. Ding, 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 ding. And you can see across the world what that actually, some of the deepest wells are showing up over here in the Middle East, at least in the cross-section line that we're following here. We didn't hit the Gulf of Mexico, where there are some actually pretty deep drilled wells that compete with this region. The last graph on the bottom is looking at the year that the well was drilled. Why does this matter? The average year of the wells. Oldest is at the top in yellow. So 2015 for most, but not all. And youngest is down here in orange, with the average again in the white line. And the average is generally running below the year 2000. And well, here we are in 2022. The older the wells, and there are some really old wells, most locations along this cross-section line, along these areas where we've interacted with the Earth's subsurface the most. The older the wells, the more likely they are degrading. The younger the wells, the more likely they are for candidates for alternative future reuse. This type of analysis, this type of understanding of this information, maybe not at the global scale, but even at the regional scale, the local scale, can really help drive insight into risk and into opportunity. But we need more data. We need more context. Depending on the questions you're trying to answer, how are natural hazards, weather events, more extreme weather events, hurricanes, even earthquakes onshore, et cetera, how are those going to interact with this record of engineering the Earth's subsurface? Our land use is changing. There's already documented issues in Dallas-Fort Worth, in Colorado, and other parts of the country where municipalities have permitted building over top of old oil and gas fields that they even forgot were there, or they thought were properly abandoned and were not, and they've led to death or other deleterious impacts. But there's also opportunity to re-engineer some of these resources for alternative future uses. Again, the hydrogen future, the oxygen storage from wind turbines for air storage for battery generation, carbon capture and storage is often looking to geologic storage as an opportunity to address climate emissions and climate change. But it all comes back to understanding the complexities of all of these different systems, having the correct information available, and being able to put it to use. So that entire World Wells effort up through 2015 was pretty manually driven. I did most of that, using algorithms and computing related work, but there was no AI. It was data science driven, but there was no AI in that. But the opportunity to do that and do it more efficiently, as you saw in the earliest slide where I was showing that AI and science was crescendoing around 2015, right around the time that I was finishing this particular effort up. The opportunity to do more in a similar drive was something that my team and I started to unlock around this time. And And this is where, I mean, I'm a geologist by training. All my degrees are geology, but I've collaborated and worked with so many other disciplines and value the opportunities to bring those pieces together to architect solutions. And this is one of those examples. We basically pivoted around 2015, 16, and started thinking about how can we do this better? Big data and the ability to use computing resources, cloud computing was really crescendoing into the mix around that time. AI and ML was crescendoing up, and the opportunity to do more with big data to fill in knowledge gaps was there, but we needed to be faster, chip away at that 2080 conundrum. So around the same time, the Environmental Defense Fund and the UN Environmental Program came to us because they'd seen part of this World Wells story. And they said, we really like what you did here. Do you think you can broaden this to encompass and help us understand the global oil and gas infrastructure footprint of the world? What infrastructure is out there? What kind of infrastructure is out there? Where is it? What's its age? What do we know about it? And what don't we know about it? Gaps are just as important to document as what you know. So we embarked on a journey, but we wanted to do it better. And so we'd been working on a tool with a computational science friend of mine called Smart Search that was a smarter way to smart search. The name says it all. It's a silly name, but I mean, that's what we were trying to do. We're like, Google search is fine for shopping history or finding something on the news, but this isn't working for finding data. We want to be able to parse the World Wide Web or parse our own servers. Or a specific website or a journal website if they allow for it. Some of them are locked down, it just depends. But we want to be able to search better and not just use keywords and not just use phrases, but actually show them things like, hey, I like this journal pub, or I like this data set. I want more of these. I like this image. I like this bathymetry data set. I like this Wells data set. I want things like this. And that's where AI and deep learning actually, Smart Search continues to evolve. We've been tinkering with it now for 6 years and putting it to good use. But it is constantly evolving and growing, but it basically uses machine learning and deep learning algorithms to assess things that you show it. It can be search terms and phrases, but it can also be a collection of data sets, publications, shapefiles, whatever you have. It uses natural language processing, TensorFlow, and other image AI parsing tools to then say, this is what here's the things that are in common around this entire data set. These things are less common, but they're in the data set. Now I'm going to go look wherever you tell me to look, World Wide Web, Enterprise Data Store, and I'm going to bring you back information that I think you want that's related to what you showed me. It's a way of parsing the digital forest and bringing back just the trees that you're most interested in. It is iterative, it's not perfect. There's a user interface that then you can say, yes, I like that, no, I don't like that, and it trains it. It's a supervised deep learning approach. We've been re-architecting it using a multi-cloud approach with Google Cloud Provider and Microsoft Bing as the search engine. There's a reason behind that, and Kubernetes driving it. But it's, the details here from a computational science effort are a talk unto itself. But it is what we have been using, and you can scale it for different purposes. You can scale it up to parse the World Wide Web. You can scale it down again to your own computer. It can search within HTML and metadata. It can search within zip files, which is actually really important because people tend to zip like data together into archival kinds of published reports. And if you're only looking at the zip title, you're losing out on what's in there. It brings back a recommendation engine that you can then use to parse through it and train it and tell it, go find me more of this, but I don't like that. Yes, no, yes, no. You do a little bit of training, you send it back out. Similar to how Google and has learned, and Facebook and others. Is this a cat? Is this you? Is those types of training types of things. I'm going to skip these just for time, but we use this in the effort for the Environmental Defense Fund in a two-pronged approach. We use Smart Search in a deep learning approach, but we also divided up the world amongst the team. There were 8 of us, and we just each took a continent and then rotated a few times. We did a manual search. We used the manual searches to also calibrate, train, and improve the robustness of the information coming back from Smart Search. But ultimately, in a 4-month period of performance, we not only went out and acquired and aggregated information from the open source, this is only open source information, from thousands of data sets spanning over 6 million features and attributes for the world that spanned transportation facilities, installation, production, extraction, and we use geology as a validation data set, because we're dealing with oil and gas infrastructure for the most part. If the geology is not sedimentary, it's probably not oil and gas infrastructure, unless it was import, consumption, refining kinds of things. And we did validate and double check, but from a production perspective, a resource perspective, which is where a lot of the features and attributes actually align to, this was useful from a validation perspective. So aggregating that information, we have all the information by point, and you can go out, the web link has been up on a couple of the slides. You can go interact with this data set in an online web application tool on the EDX platform. You can download the database, as well as the technical report that explains what we did and how we did it. But this is also just a quick snapshot of, features by country. So when you look at all the different features and attributes, the countries in yellow and orange, not surprisingly, the US and Canada are in the top tiers. Other countries here in the pinks and reds are also significant hydrocarbon related, either producers or consumers. If you look at it by density, so not just normalized to the countries themselves, but by the footprint, this is what the map looks like. And then we took it a step further. In that 4-month period of performance, we wanted to make sure that what we were doing made sense. With big data and with AI ML, there's often, it can become a little black box-ish. It is important that you can explain the result, you can validate it, and that's where the science-based or physics-based context is often very important. As experts in different domains and different disciplines, depending on what problem you're trying to tackle, bringing your expertise back into the picture and saying, does this make sense? Yes or no? And prodding at the results and understanding if the analysis adds up or if there's questions is really important. And doing validation, even uncertainty quantification and other robust tools and methods are very important as well. But you can just use your disciplinary expertise to give it a first test. And if you haven't read The Parable of the Google Flu, which is in the journal Science in 2014, I really encourage you to read it, because it's a really good caution over correlation, and it does not equal causation. Just because there's a trend doesn't mean it's real. You need to be able to explain it. And that's what we wanted to make sure we were doing. Just because we think we have data related to open sourced oil and gas infrastructure doesn't make sense. So we went back and actually developed an algorithm, which again is summarized in the technical report available to the public for download. There's a list of citations at the end. But we went back through and not only evaluated the data to make sure that it made sense relative to sedimentary basins, other validation data sets, but we also ranked each data set for their spatial, temporal, and source quality based on our expertise, and used that to help with validation of the information, but also communication of where there's likely gaps. All of these data sets have holes in them. They are not perfect. They're based on what's available on the World Wide Web in the open source. There are commercial proprietary published maps, and we use some of those for validation. We didn't include those in the analyses because that wasn't the task that we were set. But the countries that are in the oranges, reds, and yellows have more gaps, more quality issues, less features, less attributes, missing information that's just not open to the public. The countries in gray generally didn't have any oil and gas. They weren't major consumers or producers. I mean, obviously they're most countries have some sort of consumption related to gas stations, what have you, but they're not They're not the major players. We were going for the top 46 countries in this particular analysis. So we used this analysis again to make sure we understood the data, double check what we had pulled together, and give it sort of a quality, a way of communicating the quality for the consumers, so they also understood when they were using this data set that there's gaps. In the analysis report, we also have printouts of the actual features on a country by country basis, so that people get a sense of what is there from the open source record. And each montage also came with an analysis of the data density by feature class. Again, you see here, as well as graphical information around, if it says no open data, that means there should be mine data, there should be platform and wells, but it was not publicly available. And the quality rankings by that spatial, temporal, and source for the feature classes for which we actually had data available and for which we had done this ranking. Beyond using Smart Search to help with that 4-month rapid development of an open global open oil and gas infrastructure database, we've subsequently been using Smart Search for other applications as well. There's a really nice publication by a colleague of mine, Paige Morkner, that summarizes carbon storage open data resources that are largely available up on the EDX that you can access here at this URL. Her journal pub in Computers and Geoscience goes into how this data collection, what we believe is the world's largest open carbon storage data collection, was aggregated. And you'll notice that the footprint looks surprisingly like that oil and gas drilling record, because a lot of this data for carbon storage is reliant on the historical oil and gas infrastructure, or oil and gas drilling information and subsurface investigation data sets as well. There's 2 really nice studies from another colleague of mine, Madison Wenslick, that deal with metals and metallic alloys for extreme environments that also relied on the use of Smart Search to aggregate information that she was then able to use in advanced machine learning property-based analyses. Just another example of how to use this type of search information to seed a project and get more out of your analyses, so that you're not just stuck with the data that you have in hand. And you can move things forward more rapidly. So just in the last bit here, there's this huge opportunity, not only with Wellbore data, but just data in general. There's a lot more out in the historical record and online and in other archives that could be put to reuse. Our team, again, we spend a lot of time in the bottom part of the pyramid playing around and finding information and figuring out better ways to pull it together, and putting those tools out into the public forum so that folks can put them to use as well. There's Smart Search, but we also have 2 other tools, Smart Parse and Living Database, that are chipping away at these challenges in various states of maturation. But we also work on how to use this data. And I just want to drop a couple teasers. Not going to be able to unpack this, but I put the links to, or the references in case people have interest. This information is important. And the irony is most of this program, including the Energy Data Exchange itself, launched because of the Deepwater Horizon oil spill. Nobody wanted that to happen, nobody. But when it happened back in 2010, cloud computing was just emerging from the DoD side of things and becoming a major tech commercial asset. Dropbox and Box they were just thinking about deploying. Those types of information sharing tools, federated information tools, were just coming up on the commercial side of the sector, and they had not yet made their way back into the R&D realm outside of the DoD space, which is a bit of an exception. And the folks that were set to, USGS, Department of Interior, MMS, DOE researchers, including my boss at the time, that had to come together and work to figure out how to stop this thing. They were frustrated. They couldn't share information. They couldn't find the data that they needed. It wasn't easily findable. They couldn't get it into the right formats. And they were facing the world's worst environmental disaster, arguably, next to maybe Chernobyl. And they wanted to stop it. Everybody wanted to stop it. And I remember a seminar that I went to at Oregon State 10 years ago now, but the hydrogeologist from the USGS Menlo Park that was on this response team, he had to fly back to Menlo Park from Houston because of a family emergency. And they thought they had the well shut in, but they needed him to make the call. So Stephen Chu, the Secretary of Energy at the time, could confirm for the president and for the nation that they had succeeded in recontaining this well. And they did it by sending him a picture of a screen on his phone. They texted him the shut-in pressure graph. And he made the call based off a text message picture, because that was the limits of information sharing that they were dealing with at that point in time. And my boss came back from that meeting, and from this whole thing, and he knew I was working on the predecessor to EDX, a data warehousing effort. And he said, we got to do more. And I was like, great, let's do more. Let's prevent this kind of stuff in the future. Let's do things with data. So in addition to all this data resurrection and access related activity that my group is involved in, and that I'm a huge advocate for, and I'm pushing on DOE as a whole to adopt more and more of these practices, because they're so important. There's this great team that I showed at the beginning, and we've been chipping away. Alec Dyer and his co-authors here, this is a pub out just this year that's looking at this aging wellbore. I'm sorry, this is the platforms. They're now looking at the wellbores, but the aging platforms in the offshore environment. Again, there's a potential for reuse, but there's also potential for risk. Increasing mid-ocean events like hurricanes, submarine landslides, can have real environmental impacts that are long lasting, as well as just wear and tear on these things. And the analyses that they were able to do with the data that's available, using data science and machine learning to forecast platform longevity and likely removal age, so that you can avoid these types of deleterious events, but you can also look for opportunities for reuse, is something that I want to put on your plate as an opportunity. Data is the fuel for this type of research. And your expertise as scientists and engineers is also equally important. We have similar efforts that are afoot. This is an effort out of our team that's looking at ocean geohazard, basically submarine landslide forecasting, using machine learning and AI related and data related analyses, buzzword bingo there. But now we're part of a multi-agency Naval Research Lab, Department of Interior, and others effort. Oh, I forgot Madison or Mackenzie has animation on the slide. Sorry. That they are doing their own models. We have our models, and this is a way to validate these types of AI and data-driven models that are sometimes big and multi-system, is to come at the problem from different angles and cross-verify with independent groups. So this is a really exciting effort that's ongoing, but is maturing quickly. Subsurface trend analysis tool is actually based on a method that I published in 2020 in the journal Interpretation, but we're now infusing it with AI ML capabilities similar to what we did with GOGI, the Global Oil and Gas Infrastructure Database. I learned from the World Wells effort, and now we're trying to make this, it's the same idea. It's basically, we know how to improve subsurface property prediction using science-based methods and data to improve forecasting of subsurface properties, even with areas with no pre-existing measured data. But we think we can do better using AI and ML to make it faster and also reduce some of the uncertainty and forecasting as well. So I'll wrap up here with the last just 2 slides. I was mostly trying to show you guys the potential. There's opportunities to work all up and down this pyramid to unlock a data-driven future for the subsurface and the engineered components of the subsurface. While the oil and gas industry, it has its up and downs, it always has, but there's so much more that humans are trying to do in the subsurface with groundwater, storage, climate, and environmental risk, societal related challenges. So the opportunity and the need for more and more work down here is huge. So I just hope that I've catalyzed some of your own creative thinking on what maybe you could chip away at, and it starts bit by bit, step by step. We didn't have any of these pubs a few years ago, and this is some of our group's effort, but I'm putting it on the slide so that if you want to go back to the video, you can grab these pubs from here. This is a bibliography of everything I think that was cited up in the upper slides. And I want to remind you, it takes a team. I'm representing this work here. I have a grand time and the honor of working with the most amazing group of people. But it does take a team, and it takes asking, what if I look at this? I wonder if I could answer this. And pulling together folks that you can rely on to complement your expertise, and step by step chipping away at the problem and architecting a solution. So I appreciate your time, and I will pause there with about 8 minutes before the hour for questions.
All right, Dr. Rose, thank you very much for your informative presentation. What we'd like to do now is let's give students the first opportunity to ask questions. Any questions by students? Jose, Julian, go ahead.
Thank you. First of all, thank you so much, Dr. Rose. Great talk. I have a question. So are there any plans to standardize the data sets? That is, so they are in the same format for similar tasks, similar to what the International Organization for Standardization does? If not, what do we need so the global community start talking in the same language regarding the data sets? Thank you.
So it's a great question, and it's a tricky one. You already kind of foreshadowed some of the answer. So when you say standardization, there's definitely elements that can be standardized, and some data lends itself to standardization more than others. Geospatial information, there are very specific metadata standards that have been set for and agreed upon by the geospatial data community. But they've been working on it for a really long time. And it drives even them, like within the community, they'll be like, oh, FGDC metadata standards, because it's a lift, it's an effort. It's no different than putting together a journal pub manuscript. If you're publishing a data set, it is important, it takes time. If you're doing it right, you have to document it with the appropriate metadata. And it's a big lift, just like a journal pub. But many data sets are also challenging because it depends on what you personally are trying to do with it, what your team is trying to do. So you can architect standards up to a point, but then this is where we diverge from the technology commercial sector. If something is repeatable, it is much easier to architect those standards and put them in place and come to agreement and say, yes, for satellite imagery collection, we're going to agree to these standards. For sensor information streaming from stoplights, we're going to set the following standards because it's repeatable, and folks can come to agreement that yes, we need to have these things. But science and engineering related research tends to be more exploratory, and sometimes we color outside the standard lines. So there will always be some lift on the collection of that data, the types of information that you need, and you may have to, you will most likely have to do still some data smoothing here and there to make things work for what you are trying to do. There are a growing number of efforts to set those standards, and it's largely driven by the commercial sector, which is what we tend to look towards. We're trying to catalog a lot of those standards now on the Energy Data Exchange and our reference shelf, to help people identify what those are so they don't have to recreate that wheel. But I encourage anybody that's dealing with data to look to your own community and look to see what standards they have already been adopting and using. Climate data has standards. Again, satellite imagery data has standards. If you can lean on what exists and then augment and tweak as you need to, that's better than trying to reinvent the wheel. And so that's a complicated answer to a complicated question.
Thank you so much.
Yeah,
thank you, Julian, for the question. Any other questions from students? All right, I'm going to open it up to anyone, faculty and students, to ask questions. Any questions? Dr. Ravi Kumar, please go ahead.
Thanks, Michael. Thanks, Dr. Rose. It was such an excellent presentation. I was glued to every single slide you had to show with all the data. one of the questions that so I work on looking at sustainability associated with the oil and gas supply chain, and one of the challenges, especially with historical data in places like India and Japan and Southeast Asia in general, is that many of the primary documents are often not in English, and that's becoming a huge problem because right now we are manually trying to translate some of that information. And I was wondering if you had some thoughts on how we would go about doing that, considering the different languages these documents are in.
Yeah, we've in the global oil and gas, infrastructure report, the Rose et al. 2018, we actually used Google Translate for some of our, we wrote an algorithm, and it's the appendices in that report are pretty extensive. There's an appendix in there that talks about the language translation that we did. Now it's fairly rudimentary for that one. I mean, it's almost 6 years ago that report was assembled. But there's also, I know Spacey and Word2Vec and some of the other natural language processing related algorithms have been increasingly integrating language translation capabilities in. Now, the challenge comes down to they tend to be more aligned to, again, natural language as opposed to technical language, but you can train it. And they often, those algorithms, I don't know if you're familiar with those natural language processing algorithms, but they generally allow you to train it and incorporate that kind of specific subject matter discipline, technical language into your toolkit over time. And that's something we have to do, even with Smart Search and Smart Parse, where we are training those until we have confidence that the information that's coming out is the way that we want it. So the oil is actually talking about the energy resource oil and not fryer grease oil or some other kind of oil, because oil can mean a lot of different things. And that's not a particularly technical word, but it's one of those ones that has a very specific meaning within the domain that we're looking at. And I suspect would also, the other thing that we tend to do with Smart Search and Smart Parse, the two tools that we've been developing, is use context. So not just focus on the single words themselves, but look at the context around it to help the algorithm learn and be more accurate about the result that it's bringing back. And that maybe something technique-wise, if you can build that into your effort for translation, that may help as well.
Awesome. Thank you very much for that. Kaivan, I see a question.
Yes, thank you, Dr. Rose. Great presentation. My question is, are there any instruction manual or like tutorial videos on how to work with these databases available to the public?
Well, so the World Wells database is now integrated into Goji itself, and the link for Goji is in the slides. The metadata up on EDX includes information contextually for the global oil and gas infrastructure database, and the manual is the technical report, which is referenced and linked through the database as well. So for that specific one is yes. With regards to some of the other studies, STA, OGA, and the AIM infrastructure modeling tool, those data sets are also available up on the Energy Data Exchange. If you just drop the SAMI off the bottom of the URL you see on the screen, that will take you to EDX proper. If you replace SAMI with offshore, a lot of those latter studies are tied to our offshore program, and it will direct you to the information on the offshore program. So most of that is up there. It just requires that you poke around and grab what you want.
Great, thank you.
And if you have trouble finding what you're specifically looking for, feel free to shoot me an email. I'll sync you up either with the information or with one of the guys on the team that can connect you up.
Dr. Rose, I can't help myself. Since we talked about AI, I got to ask one fun question here at the end. Okay. Will AI replace subsurface engineers and geoscientists?
I mean, maybe someday, but if you go back to the Industrial Revolution, the Luddites were fearful that they were going to be fully replaced. And in some ways, yes, the manual labor of the time, weaving, et cetera, by hand was replaced by machines, but there was always something more that came next. And I think in our lifetime, these are complicated systems. If you didn't catch it, there's really very little in what I presented that's what would qualify as unsupervised machine learning, where the machine is actually doing the learning and deriving insight on its own. It's incredibly important, in my opinion, for applied energy, applied science, applied engineering related challenges. There's so much we still don't know, and there's so much that we have to constrain, that the subject expertise to explain it, to make it trustworthy, and to verify that it's doing what we think it's doing is still going to be very relevant. And I do think, Michael, that there's still, and folks here, that there's always going to be something for the expert science and engineer geek to sink their teeth into.
I agree completely with you, Dr. Rose. I like to say engineers and geosciences will do more engineering and more geoscience with the support of AI. Thank you very much for visiting. Dr. Prodanovich, I see you're off mute. Did you have a question or comment?
I was about to say, I heard loud and clear that you need feedback in this, and feedback from those who know the data.
Yep. And I put it at the beginning. Because of the infrastructure bill, because of the activities that are going on, we are recruiting. So I encourage you to go to the SAMI website, or you can shoot me an email and I will redirect. But I'm very much sincere. Full-time and intern positions, we are definitely looking for candidates, and my colleagues at other national labs and across DOE are also looking.
All right, Longhorns, take note. Thank you very much, Dr. Rose. We appreciate it. We owe you some barbecue in Austin. We'll have to make
I would love to visit Austin sometime when it's not like a 24-hour turnaround, because I've been there twice and I've yet to see the pink marble in person. So.
Right.
Oh my, that's then a weekend trip. Let's plan on it.
Sounds awesome.
All right.
Thanks everyone for your time.
Thanks very much. We appreciate it. Another